Okay, gang. Looks like it is noon. So let's go ahead and get going. All right. So what we're going to do today is we're going to finish up the final sort of named reaction in chapter 23, and then we're going to begin chapter 24. And so the type of material is going to change drastically. We're going to go back to the more familiar, all right, here's a functional group. Here's how we name the functional group. Here's how you synthesize the functional group. So if you're getting tired of all these sort of complicated mechanisms, then you'll get a little bit of a relief starting today with that, okay? All right, so as I said, last one to go over. It's called a Robinson annulation reaction. Okay, now if you wonder what an annulation reaction is, I had to look this word up, so don't feel bad if you had to, but what that means is that means to form a ring. Okay, the big fancy word for forming a ring. So that's what we're going to do. And we're going to use two reactions that we have talked about so far. The Michael reaction, and we're going to couple that with an aldol condensation. So things that you have seen before, we just need to put them together. It combines a Michael reaction with an aldol reaction. All right. So what we're going to do here is, and I'm going to draw and erase a little bit to keep it a little bit organized, but so you can choose what you want to write on your notes there, because some of this you've seen so many times, you could perhaps skip some of it. But we know that this is a strong base right here. This alkoxide is a strong base. And so it's going to grab that hydrogen right there because it's more acidic. It's the most acidic hydrogen around because the stabilization it gets from these two adjacent carbonyl groups, that enolate ion. So when it pops off, you're going to have a lone pair of electrons and a formal negative charge. Okay, so now with that, I'm going to go ahead and I'm going to erase part of this. Okay, because what we're going to do now with this carbanion, this is going to act as our nucleophile. Okay, and it's going to attack this alpha beta unsaturated, enone situation here. There's your alpha, there's your beta, and remember that what it does is it attacks the beta carbon, forms a bond with that beta carbon. So that's your electrophile. And remember that we also had the two names, the two other labels that we could ascribe to this. This is our Michael donor, and this is our Michael, I'm just going to put M, acceptor. Okay, so keep all that vocabulary in mind. So what we do then is we form this bond between this position where the lone pair of electrons I've shown and that right there. So I'm going to redraw this right here. So I'll draw my 5-membered ring. And we got the ketone group there. And we got the methyl group. Okay. And then down here, we've got this other carbonyl group right there. And that becomes important. So let's make sure we draw that. Okay. And now let me highlight this with a different color. So since it forms a bond with that carbon, I'll draw the rest of this in blue, so just so we can keep track of things. So it's going to form a bond with that carbon, which is attached to this other carbon right here. Okay. And so now I'm going to move down because that's attached to a carbonyl, okay, which is attached to this methyl group. Okay, so again, this is the alpha, and that's the beta, so alpha, beta. Okay? All right, well, one thing to keep in mind is that there are 3 hydrogens here. I'm just going to draw one of them again in an attempt to kind of keep it nice and neat. But then if we were to subject this to another equivalent of the sodium ethoxide, we've got that strong base there, that ethoxide. That's going to act as a strong base and grab that hydrogen. Okay? And then that's going to produce a nucleophile. So once again, if you don't mind, I'll erase that part. We'll kind of cut to the chase. where we get that carbanion right there. And again, the reason why that is because that is that's also an alpha position, right? So those hydrogens there in that CH3 group are more acidic than typical carbon-connected hydrogens. So we form this resonance stabilized enolate right here, which is going to attack. Now, this is the annulation part. We're going to form a ring, okay? So, and this is going to be a 6-membered ring. If you start numbering, that's carbon 1, that's carbon 2, that's carbon 3, that's carbon 4, that's carbon 5, and then that's carbon 6. So it forms a 6-membered ring. So I'm going to go back to red, and we'll draw the 5-member ring. That's really bad. Try that again. 5-membered ring attached to a 6-membered ring, and then we'll just kind of put stuff around it in the right place. So we still kept this ketone. That was unreacted, so right there. Okay. And then we've got, if this is carbon 1, and this is 2, and 3, 4, 5, 6. Okay, on carbon 5, we've got that ketone group. Okay. But now, because this nucleophile attacked that carbonyl group right there in carbon 1, that becomes, after it's been protonated, a hydroxyl group. But remember, this is the aldol reaction. This is the aldol reaction. But it's like an intramolecular aldol reaction. Okay, so we form that bond between carbon 6 and carbon 1, and then it gets protonated, okay, because the electrons move from that pi bond up into the oxygen, and then that just grabs the hydrogen from the solvent. Yes?
Why did it bond to like the purple and not like the purple? Yeah.
Okay, hold on just a second. Let me pause the recording. Okay, so for the sake of the recording now, let me just illustrate what I've changed. So this methyl group right here is this methyl group right here. And then when I form this bond between the Michael donor and the Michael acceptor, that's this bond right here. Okay, so that's the beta carbon, there's the beta carbon, there's the alpha carbon, there's the alpha carbon, and we keep going. Okay, but I am still missing I got to draw a red line. Okay, and by the way, I'm gonna bring up the nicer version. I just wanted to talk through the mechanism a little bit. Okay. All right, but again, and then if I heat this up, remember that with the aldol condensation, what we're going to do is we're going to do an elimination reaction. So there's a hydrogen here, and we've got that ethoxide around. It's going to act as a strong base, and that's going to grab that hydrogen, which is going to dump its electrons into the bond between carbon 1 and 6, and this is going to act as our leaving group. Okay, so that becomes our leaving group. And then ultimately what we form is the 5-membered ring with the ketone, with the methyl group, I won't forget it this time, and then the 6-membered ring. And then I form the double bond there. Okay? All right, and remember the reason why this happens, this aldol condensation part, is because you get the ene-one. Okay, and that has added stability, lower energy because you have that conjugated di-ene kind of setup where there's the double bond, single bond, double bond. It's lower in energy. Okay? All right. So let me clear all that out and bring up a much nicer drawing of it. But part of the reason why I didn't want to go straight to this is because it does skip some steps. And we have the Michael donor reacting with the Michael acceptor to form that bond right there that I'm highlighting now. And then this strong base removes a hydrogen from this methyl group. So it acts as a nucleophile on that carbonyl group to give us the alcohol group. And then we heat it up and we get the condensation reaction. So remember that there was a ketone here. Remember that, and again, if you don't remember the step-by-step mechanism, that's okay, as long as you remember ultimately what happens in an aldol condensation. So this ketone group becomes a carbon-carbon alkene group. And so whatever the the nucleophile that's going to keep its ketone group. So this was your nucleophile, or it comes from the nucleophile. It stays the same. But whatever was your electrophile, in this case, this ketone group, it ultimately becomes a carbon-carbon double bond. All right. Okay, now to complicate things more, as if we needed that, but sometimes there are multiple potential products, and so you got to be on the lookout for that. And the thing here is that it really goes to the wording of the question. 99 out of 100 times you'll see it, just what's the major product? And so sometimes you got to make sure that you consider all of the multiple products because the major one will be the most stable. And just talking through this one again, so you can see what I mean by that. I'm going to show you the product that's shown, and then show you an alternate product as well. Okay. So skipping some steps like before, what we have here is this is going to be the source of our nucleophile. So they got that lone pair of electrons, right? And this is your alpha beta unsaturated. So it's going to attack that beta carbon and form that bond. Okay. Oh, and also, yeah, so we're going to form that bond right there. That's the bond that's been formed. Okay. So that's your Michael addition reaction. And then if we just do the aldol reaction, the aldol condensation, in this case, what's happening is this has got hydrogens on it, right? And so one of those gets ripped off. It's got 3 hydrogens on it, so I'll just draw 2 of them, because one of those gets ripped off and gives you your nucleophile, which attacks that carbon. Okay, and again, with heat, usually it's like sometimes you don't have to add heat to get the aldol condensation, like in our case with the lab that we did, but it always is good to show it because that's that clue that it's going to drive the aldol condensation reaction. And so since this is your nucleophile, it remains unchanged. It's still the carbonyl with the CH2, so the carbonyl with the CH, in this case, it's just CH. But because H2O is the byproduct, so, it splits off of water, the minus H2O. Okay, and what disappears is that carbonyl in your electrophile, the acceptor part. Okay. All right, so that's one product. Okay, but I want to point out another potential product, just to illustrate this idea that we could have multiple potential products that we need to keep in mind. All right, so you'll remember that from the first example, this first top line here, we took a hydrogen because it's at the alpha position there, so that one of those hydrogens was removed. Well, there are other alpha positions, like here. That's an alpha position relative to this carbonyl. So there's 3 hydrogens. We got, that's a CH3 group. And so again, I could form, I'm going to cut to the chase and just show you, if I rip off one of those hydrogens, that creates a carbanion. Okay, so that could attack the other carbonyl. So in this case, your nucleophile is this part of the molecule, whereas in the first top line here, the nucleophile was, we can talk about the green versus the pink. So the one we're doing now, the nucleophile is alpha to the green color-coded oxygen. The one we did previously, the carbanion was alpha to the pink color-coded oxygen. So just to keep it straight. Okay, so then what happens is, if we number things, well, since I have this labeled alpha, I think that's probably still good enough for now. So draw the 6-membered ring. Because remember, this only happens if you form 5 or 6-membered rings. Okay, and so this is going to be still our okay, and this is that alpha carbon. So it formed a bond here. So this alpha carbon forms a bond here. So that's this bond I've drawn right there, and this becomes an OH group. Okay, And then that still stays the CH2, that still stays the CH2. And then over here is where we have the ester group, the CO2 ethyl ester. Okay, let's make sure I got everything. Okay, and I'm going to change colors just to, again, highlight this. So here at this alpha position, now I still have 2 hydrogens, and I still have some strong base around, some of that sodium methoxide. Okay, so it can grab one of those hydrogens, which will dump its electrons into the bond between those 2 carbons. The OH group will leave. Okay? And you see the difference here in just a second. So now, okay, so this is gone. So that becomes a double bond. I still have the 1 hydrogen there. That's my alpha position. Okay. Oh, the other thing that I have forgotten is, yes, so in this one I left out, unfortunately, I did the same thing I did with when we had to stop the recording. There's a methyl group right here. Okay, so draw that in. And so that methyl group is still right there. Okay, so you can see the difference between these 2 potential products. Here, the ester group is directly across from the methyl group. Up here, the ester group is directly across from the ketone. In this one, the ketone and the ester group are adjacent to one another. Up here, the methyl group and the ester group are adjacent to one another. So the point being is that you do have to keep in mind that there are multiple potential products. I don't know which one of these would be considered the major product, because normally what you would do to decide that is how substituted the alkene is. But both of these are tri-substituted. So this one is tri-substituted, and this one is also tri-substituted. So it would probably be based on just the steric effects. Which is worse, a methyl group next to an ester group or a ketone next to an ester group? Whichever one is less stable, that's the one that is most likely to not be the major product. Okay? All right. I don't think I'm bringing up a nice, pretty drawing of this one. So is everybody good to go on that? Okay. And everybody got that other methyl group in there that I forgot to put that methyl group right there? Okay. Okay. So that is the Robinson annihilation. We'll do, hopefully out of time, we'll have to do one more for practice, but not right now. Right now, what we're going to do is we're going to move on to chapter 24. Oh yeah, here it is. I did draw this nicely and bring it up. This is the other potential fighter product. But again, it's the same idea that the ester group and the ketone group are right next to each other. In this case, here, the ester group and the ketone group are directly across from each other. All right, so let's talk about amines, okay? What are they? Well, they are derivatives of ammonia. So just like alcohols and ethers were kind of like a water molecule, instead of HOH, it could be an ROH for an alcohol or an ROR for an ether. We can do something similar with amines. We can substitute hydrogens with carbon groups, alkyl groups, acetyl groups, whatever, aryl groups. So they are alkyl substituted or aryl substituted derivatives of ammonia. Now, because there are 3 hydrogens we could substitute with an R group, we need to classify the amines as either primary, secondary, or tertiary. So one thing we'll notice, though, is it's a little bit different than the way we did it with an alcohol. With an alcohol, for example, a tertiary alcohol, tert butyl alcohol, that was the carbon the carbon that is attached to the OH group. How many carbons is it also attached to? And in this case, this carbon that has a bond with the OH group is attached to 3 other carbons. Well, with amines, it's not the same. It's just how many carbon groups are attached to the nitrogen. How many hydrogens have been substituted on that nitrogen. So if there's 3, that's a tertiary amine. Okay? If there's 2, that's a secondary amine. If there's only 1, that's a primary amine. But you also can make a quaternary amine, and that's shown over here, but it's always going to be a salt, an ionic compound, because whenever you put that 4th group on the nitrogen, it will adopt a formal positive charge. And then you have to have some sort of anion, some negatively charged ion to counteract that. So those are known as quaternary ammonium salts. Those are compounds that carry a positively charged nitrogen atom with 4 attached groups. Okay, so as before, we'll go through the introductory material such as naming. So simple amines are typically named by just throwing the suffix amine on the name of the alkyl substituent. So if the alkyl substituent is a tertiary butyl group, a tert butyl group, or T-butyl group, you see that in different ways, you just say tert butyl amine. If it's a cyclohexyl group, you could just say cyclohexyl amine. Okay? If there's multiple of that type of group, like 2 or 3, then you can just also use the numeric prefixes like di and tri. So symmetrical secondary and tertiary amines are named by adding the prefix di or tri to the alkyl group or the aryl group. Like in this case, it's diphenyl. These are aryl groups. There's 2 of them. They're identical, so we would just say diphenylamine. This has got 3 ethyl groups, so we would just say triethylamine. Okay. Well, what if they are not the same? In that case, you need to pick the one that's the longest and name it according to that. And then you would name the other substituents on the nitrogen on their own, but with an N in front to indicate that they're attached to the nitrogen. So unsymmetrical, substituted secondary and tertiary amines, first of all, named as N-substituted primary amines. So, we kind of pretend that it's a primary amine, but then we load it up with prefixes to indicate that it's a secondary or tertiary amine. And you name it based on which substituent is largest. So the largest alkyl group is the parent name, and the other alkyl groups are just considered as substituents on the nitrogen, N substituents. So, for example, you got 2 examples here. So we've got a methyl group, we've got a methyl group, and we have a propyl group, a 3-carbon group. So since the propyl group is the longest one, we could just call it propylamine, and then the other 2 are called N,N-dimethyl. So N,N-dimethylpropylamine. Okay, in this case, the largest one is a cyclohexane ring. So that's the parent name, cyclohexylamine. And notice that we've got 2 different substituents on it. One's a methyl, one's an ethyl. So you need to indicate how each of those are attached to the nitrogen with their own capital italicized N. So N-ethyl, N-methyl, cyclohexylamine. And again, we're using where we put these in alphabetical order. So E comes before M, so it's N-ethyl, N-methyl, cyclohexylamine. Okay. So the other thing that we can do is we can do it more as a suffix rather than as thinking of it as a group, an alkyl group. So the suffix amine can be used in place of the final E of the parent alkane. So something like this, if you have a dimethylcyclohexane, we could just call this dimethylcyclohexaneamine. That's how you'd say that. I left out the 4,4 part, but 4,4-dimethylcyclohexaneamine. So you see, we just took the normal alkane name. If this was just a hydrogen rather than an NH2, whatever that alkane name would be, we just changed the suffix to amine. And here again, we've got butane, 1, 2, 3, 4 carbons, so butane. But it also has 2 amine functional groups on it on either end, so we would number it 1,4-butane diamine. Okay? Now, alkanes, or pardon me, amines are kind of like alcohols in that they're most often just treated as a substituent, and even like halides. Most of the time in the naming, they just end up getting incorporated into the name as a substituent. And you have to do that when you have multiple functional groups. So amines with more than one functional group are named by considering the NH2 as an amino substituent. And remember, that means it becomes a prefix rather than a suffix. Everything at this point, up to this point, we've talked about naming it with suffixes. Now, because other functional groups are present, they have more importance, they have priority, the amine part becomes a prefix. And we just number it, and we say amino. So that's how you indicate it as a substituent, is that it goes from amine to amino as an amino substituent. So for example, you got 3 examples here. This is butanoic acid. So there's 4 carbons in it. It's got a carboxylic acid functional group. And on carbon 2, you've got an NH2. So that's 2 amino butanoic acid. Here we've got a benzoic acid. So the parent is the benzoic acid. And it's got 2 NH2 groups on it at the 2 position and the 4 position. So 2,4-diamino benzoic acid. Okay, and in this case, we've got, again, 4 carbons where a ketone group is on carbon number 2. So it's 2-butanone. But then on carbon number 4, there's that NH2, so it's 4-amino-2-butanone. Okay, so shifting gears a little bit, amines can be incorporated into a ring, and we would call those heterocyclic compounds. Anytime that a member of the ring is not carbon, it's called a heterocyclic compound. So heterocyclic amines are compounds in which the nitrogen atom occurs as part of a ring. Now, the difficult thing is it does involve some memorization, because each one of these rings, these potential rings, has a common name. Okay, so each ring system has its own parent name. Okay, so yes, you do need to put a little bit of effort into memorizing these. This is one of those flashcards you just look at 5 minutes before your test, so you just, it's fresh in your mind. And at position 1 is where the nitrogen is, always. Okay, so some of these are real familiar with, like pyridine. Okay, but others are less familiar. Okay, so let's just think about these. I'll let you go back and look at your notes and kind of come up with names for these 2 guys. I'll let you check your work in just a second. And that first one, it might be better to actually redraw it. Might help you. Okay, so you want to check your work. As I said, I rather than this, one line entry condensed form, I redrew it right here. So the NH, that's the NH. It's got a methyl group on one side, there's a methyl group, and then this ethyl group is right here. So you go with the longest group, the largest group as the parent name. So this would be called ethylamine. And then also indicate that there's a methyl group on the nitrogen, so N-methyl ethylamine. There are other ways you could name it, potentially. You could call this ethanamine with N-methyl ethanamine. You wouldn't have to do it as ethyl. You could do ethanamine. Well, right, because that's only when you have to choose between prefix names. In this case, there's only one prefix, really. Technically speaking, there's only one prefix on this one, the methyl. Yeah. Okay. All right, so some of the properties of amines, now that we're done with naming, we'll just review some things here. That you can see down here in the picture that it's going to be tetrahedral, sp3 hybridized. In terms of solubility, amines are typically pretty soluble if there's 5 carbons or less in the structure. And it's because of that lone pair of the nitrogen can engage in hydrogen bonding with water molecules, so that's why it's going to be at least somewhat soluble in water. And if you want to really enhance its solubility in water, then all you need to do is protonate it. So that's what that next bullet there is. Protonating amines to form an ammonium salt is a common way to enhance their solubility in water. This is actually done a lot with, a lot of medications are these nitrogen-containing compounds. But in order to make sure they make it into your bloodstream, which is a water-based fluid, they protonate it with HCl. And so the medicine that you actually take is the medicine, the active compound, but protonated with hydrochloric acid so that it will actually, dissolve in the bloodstream. Okay, and again, because of the hydrogen bonding, the potential for hydrogen bonding, that you typically will have elevated boiling points. And especially if they're primary or secondary amines, because those have even more hydrogen bonding because they also have that NH bond that can engage in donating hydrogen bonds. So the lone pair can accept hydrogen bonds, but if you do have NH bonds, like a primary or a secondary amine, they can also donate hydrogen bonds, and that elevates the boiling point. That's it. Okay, cool. All right, so let me end that.